number 10 is an interesting problem because we're taking the limit as h approaches 0, and notice it's an integral. Well, if I just plug in h equals 0, okay, I get the integral from 0 to 0 squared, which is 0, f of t dt, all over when I plug in 0, 0. Well, the integral from 0 to 0 grabs no area, so this is 0, and then the bottom is 0. That just basically tells me L'Hopital applies. So what I'm going to do is I'm going to take the derivative of the top. So I'm going to take d dx of, actually d dh to be correct, d dh of the integral from 0 to h squared f of t dt. Okay, and then I'm going to take the derivative of the bottom, which is just 1, and then redo the limit and see if anything works out better. Okay, the derivative of the integral, remember, just cancels the integral. And then what I'm going to do from the second fundamental theorem is I'm going to plug this in where I see the t. So the top really just becomes f of h squared times, don't forget there's the chain rule of that limit, times 2h all over 1. Okay, so now what happens if I take the limit as h approaches 0, here I get f of 0. I don't know what that is, but times 2h, which is 2 times 0, so it looks like the limit, regardless of how you look at it, will be 0. Question number 11 says, for what value of c does this function have a relative minimum? Relative minimum, right away, tells me to find the first derivative. So if I take y prime, c is a constant, so the derivative of cx will just be c, plus, and then keep in mind this term is really 3x to the minus 1. So instead of a plus, actually, this should be a minus 3x to the minus 2, okay, equals 0. To have a critical number, I need this to equal 0, so I'm going to move the 3x squared over. So c is going to equal to 3 over x squared. Multiply both sides by x squared, kind of switch things around, you're going to get x squared is equal to 3 over c. So that the critical number, which we want the critical number to occur at 2, right? So we're going to plug in x equal to 2. So instead of x squared, it's going to go 2 squared, okay, is equal to 3 over c. So I got 4 is equal to 3 over c. Multiply both sides by c. I got 4c equals 3. And you can see that c will equal to 3/4. You should technically check if it's a relative minimum by doing a sign chart. Question number 12. It says that the function has this characteristics. Y prime is greater than 0. Which tells me it's always increasing. Okay, the next characteristic, y double prime is less than 0. That tells me it's always concave down. So I just need to find a function that's increasing concave down. Well, this is concave up, so that's out of the question. This goes from concave up to concave down, so that's out of the question. This one is concave down, but it's decreasing. It looks like the only choice that really makes sense will be B. Question number 13 says to find this limit. So obviously this is testing our L'Hopital knowledge. If you plug in infinity to the top, I get ln of 1 plus infinity, which is just going to be infinity. If you plug it into the bottom, it's infinity squared. So you get infinity over infinity, L'Hopital applies. So that tells me that then this is equal to, the limit as x approaches negative infinity. The derivative of the top is 1 over 1 minus x times, don't forget there's a chain rule because the derivative of the inside is negative 1. All over, the derivative out there is 2x. If I rewrite this a little bit, this becomes a limit as x approaches negative infinity. I'm going to move the 2x down to the bottom here and treat it as a 1 over 2x. So there's a negative on the top. There's a 2x, and then there's going to be a 1 minus x. The point being, when you plug in infinity, this tends to 0 because you get infinity on the bottom.